Okay, so this is part 2 of the video recap of module 3. So in part 1, we kind of went over the regression assumptions as well as some examples of the ideal residual plot, as well as a couple of examples where some of the regression assumptions are not met. One thing I'll mention in simple linear regression, so only if you have one predictor variable, one can actually use the scatter plot of the variables as well to assess if the regression assumptions are met. So let's take a look at examples. So this is going to be the example from your tutorial. On the left here is the residual, the scatter plot, and on the right is the residual plot. And for the scatter plot, I overlaid the regression line, and on the residual plot, I overlaid the horizontal axis over here. Now, if you take a look at this picture on the left versus the picture on the right, the residuals, right, measure the distance between each data point from the regression line. So if you notice this cluster over here of 4 data points where they are all below the regression line, then in this instance, these residuals will all be negative. So this cluster of 4 actually corresponds to this cluster of 4 over here, right? And then you have this cluster of values where they are on the left, they are greater than the regression equation. So all these residuals will be positive, and so these correspond to these values over here. And then you have this cluster of 1, 2, 3, 4, 5, 6, right, which will have negative residuals. It's basically 1, 2, 3, 4, 5, 6, right? And then this one over here, which is negative, is that one over there. So really, right, we said that in the residual plot, we want to see an even scatter on both sides of the line. So you want to see an even scatter on both sides of the line, right? So in this case, for the really small values, right, we don't have anything on this side, right? And for all these values over here, right, we should have a bunch of data points over there, and that's missing. And likewise, right, all these are clustered over on one side and not on the other side. So that's what we would want to see over here. The one thing I'll say, right, is if you kind of imagine this is your regression line, and if you kind of rotate this line and rotate everything such that this regression line becomes the horizontal axis, you will get this plot over here, because that's the residual and that's the residual over there. So on the scatter plot, you want evenly scattered on both sides of the line, variability to be constant as well. So we could use the scatter plot as well, because the residual plot is basically like a reorientation of the residual plot. But this only works in simple linear regression. So some general rule for data transformation. So residual plots can help us detect issues 1 and 2. So as a quick reminder, issue 1 is whether the average is 0, and issue number 2 is whether the variance of the errors is constant. So residual plots can help us detect these two issues, and data transformations can be used to deal with these two issues. So transforming the response variable is performed to handle issue number 2, the constant variance issue. A successful transformation of the response will result in a residual plot. So if you choose the right transformation, then the resulting residual plot with the transform y should result in a residual plot with constant variance. Transforming the response variable may also influence issue 1, whether the relationship is correctly specified, or right, which results in the mean 0 of the errors. However, the choice of how to transform the response is chosen to solve issue 2. Transforming the predictor is performed to handle issue 1. Transforming the predictor does not theoretically help with issue 2. Right? So if your variance is already constant, and your mean is not 0, so your linearity assumption is not reasonable, then you want to work with transformations of the predictor. When both issues are present, we transform the response variable first to handle issue 2. And once that's handled, then if we still have not the right relationship, then we transform the predictor variable. Right, so this is kind of the way in which we handle these issues and the reason behind them. Now, why is transforming the response variable used to solve the non-constant variance assumption? So basically the reason for this is the variance of your y, right, for each value of x. So this value has to be a constant. So y we know is equal to beta 0 plus beta 1, x plus the error term, right? So this is basically y. Now, in a regression setting, beta 0, beta 1, these are parameters, so these are fixed values. And the distribution of the response is conditioned on the predictor, i.e. we view the predictor as a fixed value. So for each fixed value of the predictor, what is the variance here? So that's a constant, that's a constant, that's a constant. So the variance of any constant term is 0. So the variance of all these terms is basically the same as the variance for your errors for each value of x. And by definition, the variance of your errors for each value of x is fixed, is a constant value given by sigma squared. So this is why the variance of your errors is the same as the variance of your response. Therefore, the fixed issues with the variance assumption, we transform the response variable. So this is the reason why you notice that transforming the x will not influence the variance, at least theoretically. Another tool that we could use is the Box-Cox transformation or the Box-Cox plot. The residual plot is kind of an empirical way to evaluate assumptions. The Box-Cox method is an analytical way to evaluate whether we need to transform the y variable. So the transformation is basically the following. You're going to raise your y to the power of lambda if the transformation is, it chooses the value of a lambda that's not 0. And if lambda is 0, it's a log transformation of your y. And by log, it's the natural log. Right? So in all my notes, whenever I write about log, it's the natural log. So how a Box-Cox looks like, it looks something like this. We have a few different values over here. So the middle one here, so you notice that there are 3 vertical lines, right? This one, that one, that one. The one in the middle is the quote-unquote best value, but the other 2 are basically the lower and upper bounds of a confidence interval. And so the basic idea is, as long as you choose any value within the confidence interval, the resulting transformation should work out. So typically what we want to see, right, is the following. If we notice 1 is inside that range, then it's saying that our transformation is y to the 1, which is basically no transformation. So if 1 lies inside the interval, it tells you that you don't have to transform your response and your variance is probably constant. The other value we typically want to see is whether lambda is equals 0 lies inside the range, because if lambda is 0, then we're basically using a log transformation for the y variable, and that's preferred because, as I wrote in some of my notes, that there is still some interpretive value with your model if you do a log transformation for the response. Now in this particular situation, right, none of these values lie in the range, right? So we have values between, say, like 1.8 and 2.8, so any value. So I could choose a value of 2 or 2.5. So if I decide to say, hey, since 2 is inside the range, then it's telling me I want to square my response variable. So that's how we use the Box-Cox plot. Right, so just a few practical issues to remind yourself, right? So you should always produce a residual plot for every model that you're considering. You could also produce a Box-Cox plot to help you decide if you need to transform the y variable. And you want to assess the plots to decide which variables need to be transformed and how. The choice of transformation should be guided by what you see in the plot and not by trial and error. Transform one variable at a time, refit the model, and see if your transformation helped you solve one of the problems, right? If it does, right, then you want to keep that transformation, right? So produce a residual plot after each transformation and then assess them to see if the transformation helped in the way you intended, right? So then we will see if another transformation is needed. If so, we will kind of repeat, right, transforming one variable at a time, and we stop when the residual plot is satisfactory at the end.